So I'm going to talk a little bit about expanded beam connectors and the technology associated with that, and sort of tell a bit of a story about how we developed those at Winchester, at King's, and the different products that we developed through those. I'll repeat a bit of the stuff that Hoa said about fiber connectors, so I can skip over that, save a little bit of time, and get us out of here quicker. But the background and the history of sort of how we ended up where we ended up and how we ended up with these products is something I'll go into some detail on. And the EL video jack and expanded beam contact is sort of where we're at, and then having a look at where we go next. So we ended up with the same four connectors: ST, FC, SC, and LC. Not very creative with the connector naming in the telecom world, but those are the ones that are pretty much used everywhere now in the telco and in the datacom world. It's probably a little hard to see the ones up on the right there. There's a couple of extras down the bottom. There's an MT connector, which is the multi-fiber, and you don't see as many of those out in the broadcaster or even in the telco, but they are out there, and it increases the density. And then in the broadcast side, you have the SMPTE 304, and King's makes one of those. If you need any camera connectors, they're definitely out there. Limo is the leader in that. Another one that's coming up now is Optical, and then you have a lot of military style connectors like the 38999, the AirInc, and there's a whole bunch of military style. They were one of the first actually into fiber, because of some of the reasons with reliability, with the ability not to tap those, and on planes being so much lighter than the copper. So these are all physical contact connectors. And with physical contact connectors, you have the issue with dirt and dust. And previous speaker mentioned that a little bit, and I want to go into a little bit more about that, because that is one of the biggest issues that people in the field see when they're using fiber optic connectors. And you can imagine if you have, 380 gigabits going down one fiber, you really don't want a speck of dust getting in the way of all that bandwidth. So, you know, having things going over single fibers is great, but if you have a connector that will fail, you know, with one 10 micron piece of dust, you know, that's a very unreliable system. So even after you clean it, it can still be dirty. And if you're not good at cleaning, you can make it worse. And I'm actually going to do a demo here to show you a little bit about how cleaning works. That's why I have the big monitor over there, and hopefully it will come on. So even though we had, he did show you a static picture, I think it's a lot more graphic if you can see it dynamically. And you can see it's a relatively clean connector there. That the white part is the ceramic, and then the black part is the glass, and then the middle is the core. And you can see that's a single mode fiber, so it's a pretty small core. So you could imagine, you know, hundreds of HD channels going down that center. If I just take this connector out and touch it, you know, I ate a little bit of the Philly cheesesteak, so there could be a little bit of cheese on there or something else. But it's going to look like that, and you know, relatively clean here, but that's basically going to stop any light going through that connector. Not only will you get return loss, but you could get like a 10 dB insertion loss. And you saw the link budgets that he had before. They were, you know, around 4 dB, 6 dB, 3 dB. That's the kind of a link budget that you're expecting, you know, a headroom. And as soon as you touch one of those connectors and you plug it back in, you just lost your signal. Now if I try and clean that, you know, the old method, you rub it on the shirt, it doesn't always come clean. So a lot of people would think, oh, I cleaned that connector. And again, it's a pretty clean shirt, but it actually makes it worse. So, you know, you can try and clean it with just a tissue, and you can get a little bit better, and that will actually bring your signal back up. And so most people will think, okay, I'm back up and running, everything is fine. But rarely will you ever actually see a clean connector in the field, you know, if you have a scope like this. So, so there's only a couple of solutions really to this problem, is inspection. And if you clean a connector without inspecting it, you're probably not cleaning it. You're probably actually making it worse. Some of the products that came out, and some of the ones that Hall mentioned, and we have a couple over there, the one-click cleaners that do have a rotating clean device inside there, they do actually work pretty well. But getting people to use them and have them in the toolkit and really religiously do that is very difficult. So the other solution is expanded beam connectors, and that's where we come in. So right now there are really one type of expanded beam connector that's out there in the market, and those are the ones on the top there, the circular expanded beam connectors. They use ball lenses, they use a metal insert, they're quite large and heavy, and they do provide the benefits of not having to clean them, because as I'll just go back to this one here, as you can see in the bottom picture, it expands the size of the light beam by about a factor of about 1,000 times in terms of the surface area. So you saw all that dirt on that connector, it wouldn't really see that, you know, because the size of the beam itself is bigger than the fiber. It's actually the entire size of that screen there. The light will still get through. You know, all of that dirt that you saw on that might only give you a couple tenths of a dB of loss. So expanded beam connectors essentially eliminate those issues with the cleaning, but they bring in a couple of things of their own. You know, it's more expensive, and it's bigger, and it's harder to terminate. And so the other style of expanded beam connector is the expanded beam contact. That's in the lower picture there. You can see that it's a small device that contains all the same features of a connector, but it's in a much smaller size. And there are a few companies out there that are doing this, but none of them are really in the broadcast world. They're more in the military side. So we're trying to bring this over into the broadcast. You know, it's an area where you need the ruggedness, you need the ability not to clean, you know, because people will forget, and you want that high reliability. So with the expanded beam connectors, it reduces the cleaning issues, so you've solved that problem. But with the expanded beam contact, not only do you reduce the cleaning things, you also can do all of these other things that I listed. So you can have more contacts in the same size because it's smaller. You can reconfigure between copper and fiber by replacing the fiber connectors contacts with fiber contacts. So you can mix fiber and copper in the same connector housing. You can see on the right there. And then at least with our contacts, you can get a high return loss potential because you can use an angled connector. It's not actually a connector, an angled fiber that launches into the lens. And so you actually automatically get a good return loss. So you can use them over RF or analog video over fiber. And then the last reason, and this is actually the reason that we started this whole thing, is that it's useful for actuating a video jack. Because the whole impetus for this design was, it came about during a meeting in 2007. Winchester acquired King's, and they acquired the company I was working for, Advanced Interconnect. So they sort of brought us all together. Oh, I was supposed to take out that line in Bristol, and we all met and we said, what do you guys want to do in fiber? And they were designing a new center there, and they said, well, we would love to patch fiber. You know, we'll have a full normal video jack for fiber in a jack field and not have to worry about cleaning. You said, okay, well, that's impossible, you know, because you've got the SC to SCs and, you know, ST to STs. You've got to unplug them, and, you know, if dirt gets in there, then it's going to be wrecked. But we went away and thought about it, and they said, you've got to be able to switch it, no power, you know, get rid of the handling issues, have the full normal, and then have a decent return loss and an okay insertion loss. So these were sort of the marching orders. If you can do this, you know, we'll like that. And you can see on the right the you know, the switching, which is just a normal a video jack, and you can see below the old King's full size. A few of those have been around in the world, and these days you don't see too many, but hopefully more of the mid-size and the DIN, which is the ones that we're really proud of on the copper side. So what we needed to do was to come up with a few different tasks. We had to design a video jack, design a connector, and figure out how to align them all together to sub-micron tolerances. So, you know, easy, right? But it's not that easy. We decided, okay, we can do it with expanded beam, but we have to have a manually actuated fiber optic switch. And you can see on the right there's a little lab experiment that we actually took into ESPN, where we put it in a box in there and showed the people what we were looking at doing. And they kind of said, well, you know, is this ever going to work? Is this ever going to be a reliable product? He said, yeah, of course it is. So we went through the process, and thought it would take about 6 weeks, but you know, it took a few years. And you can kind of see the simulation that we did in 2008. We went through 2009 and actually showed this design at NAB. Some of you may have been out there and seen it. Had about 10 dB loss, and you know, it switched and it made the demo okay. But you know, then we went further, did a lot more simulation, a lot more testing, and by end of 2009, beginning of 2010, you know, we had a reliable device. And then you can see on the right there that we installed about 500 of these at a studio or a facility down in Florida, and I'll actually show a little bit more about that. So that was the video jack that we designed, and then we needed to have a connector that would mate with that. Of course, they have to be designed together, but having the manually actuated switch was a core part of that. And there was some technology that went into that to ensure that it's aligned correctly. So there was a few needs for this to make sure that it would be, we could manually actuate the switch, and then we could also have the low losses and protect the lens from the dust, water, finger and scratches. And that was really the whole thing of protecting it from making sure that it didn't have to be cleaned at all. The other thing we thought about in the future, if we wanted to make this a standard, we wanted to have the optical axis, you know, right down the middle of the tube, the contact, so that in the future we could have other vendors making contacts that would mate with ours. And expanded beam connectors don't normally have that. Each manufacturer has their own configuration of the optical axis, and it's kind of impossible to measure. You know, unless you made it with another connector, you really don't know where that is. So we made the connector with the optical axis down the middle, and did a few other things to make sure that it complied with what they were looking for. And I'll move quickly on this slide, but this was the first generation of it, and you can see the components that's made up. And really every expanded beam connector has these types of components. You have a ball lens in there, you know, you have some kind of a ferrule that holds the fiber, and then you have some kind of alignment. Now we're the only ones that have the alignment tube that's so long out the front, and that protects your lens so that you can't, so that if the dust or dirt or anything like that tries to enter the right side of that lens, it has a long way to go before it'll ever reach the lens. And you know, you can really dip that into water, you can put that into dust, and it doesn't make it down there. So, and I'll show the testing later on. It's quite it's really a unique feature of this style and this design. And some of the testing that we did on the video jack and on that contact, you know, we put it through 5,000 cycles in and out on that jack, and also put it through the humidity and the environmental cycling to make sure that it would, you know, wouldn't get any kind of condensation on the lens and those kinds of issues, as well as verifying that the design that we did and the optical simulation would actually hold up in practice. And that's why it took a couple of years, because sometimes it didn't. But eventually we did, and we put it into this dust chamber, which we, you know, built specially to shoot the dust right at the end of the contact. And you can see on the bottom left there, we basically have the prism out in the open inside this chamber, and you know, it's coated with dust. But the actual loss changes were only a few tenths of a dB. So similar to putting a dust or putting a fingerprint on, it really, you know, the light gets through and it doesn't attenuate nearly as much as you might think. You know, so after all that, we did end up winning some awards, which was nice. And at IBC in 2009, we got the Peter Wayne Award for IABM Innovative Product of the Year, and also TV Technology too. So as I mentioned, the Orlando sports site that we had was one of the big installations. They have about 80 acres down there. You know, I think 800 fibers running to all corners of that facility, but they don't have any matrix switch or router in there. It's basically all done manually. They had one rack where all 800 of those fibers come in, and then they have about 10 signals going off to their other facility. You know, and they're choosing which one to put up on the air or on their internet channel. And they were all STs, so they installed them a few years before that, and they put all, you know, 1,000 ST panels in there because it's cheap, it's low cost. You know, they figured they could do it, and they put STs throughout the field, They were having all kinds of problems with the reconfiguration, because every morning they were saying, okay, we've got a baseball game over here, you know, we've got a football game over there, reroute the, you know, repatch the STs, and you know, they had the cleaning equipment, they had the viewing equipment, but they were never really sure, you know, is the problem in the field, is the problem in the patch, you know, what's wrong? And so it would take them 3 or 4 hours to set up every day. And then once they put in the video jacks, they basically could just patch. And they didn't have to worry about dirt or cleaning, and they always knew that the problems, if there were any, were out in the field. And so essentially they just went down, they only needed 2 people, one person inside, one person outside, you know, one guy patching, the other person looking at the cameras in the field, and they could set it up in like 30 minutes. So since August 2011, they've never cleaned any of the patch cords. They've never cleaned any of the equipment. They just left it, you know, hanging on the wall, just like a copper patch cord, and they haven't had any failures. So it really, you know, we got the verification sort of in the field. So you know, based on the video jack technology and being able to put it in like a copper video jack, the idea is that you don't have to do a cross-connect or a interconnect solution, you know, like a traditional telco. What you can do is you can just put in like a broadcast where you have the patching on either side of your router, and you have a fiber in your router itself. As Ho mentioned, you know, there is a lot more density in fiber, and I couldn't believe how many fibers you can get into a small area on the transmission equipment nowadays. And that has been a limitation up until now, is that the transmission equipment required a whole lot of optical to electricals, so you may as well just patch in copper. But our idea is that then you can change over and say, well, it can just be all fiber. You know, you can have all fiber outputs on your switch, they can go to all fiber patching, and then they can go off to equipment that has fiber on it. And you know, if your equipment doesn't have fiber, you can always put a small converter. You know, there are quite a few converters out there available today, SDI to copper to fiber, and you know, and forget the copper altogether. So that was all the development of the video jack, and then that led up to the technology of being able to have a very small contact that has a full expanded beam connector inside of that. And you know, we knew that there was a good technology there, and it really could be used outside, but you know, it was designed for a video jack, which is an inside product. So we were thinking, what can we do to leverage that and get that into the outside world? And what we decided is to make that contact into a small contact that can go inside an existing available connector, like a 38999 military connector. There are other connectors like you know, 5015 bayonet style connectors. There are many military connectors out there that have replaceable contacts. And so we went down that path of saying, let's create an expanded beam contact that can be removable and insertable into traditional copper connectors. So really the requirements were relatively simple. It just had to latch in place and have something that would protect it as people insert and extract it. And you can see over there, if you saw the demonstration before, it's a very rugged little contact, you know, for a fiber contact that's that small. And some of I just sort of threw some pictures out here that just, you can see the different progression of how we developed it. You know, up on the top right, you can see the small lens and the tube that's used, and it's fully sealed in the factory so that the end of the fiber is fully protected. And you know, any expanded beam connector has to have a lens, they have to have fiber, has to have a ferrule, and the key is how you protect it. And that's something that in the traditional expanded beam connectors, you know, you would terminate them you know, in your own the cable assembly area. So you're polishing the connector, you're inserting it into the expanded beam back shell, and if you do that and you put dust in there, then you've really sort of put a latent failure out into the field. And you know, while those connectors can be very good, and if you know how to terminate them and you do a good job of it, they'll work well. You know, our idea is that you know, they should be sealed up in the factory, and they should be polished and done there, and then you can attach them to cables, and you won't have any issues with reliability in the field. So I've contrasted some of the differences between the two, and you know, I call it traditional expanded beam because there really hasn't been any other expanded beam up until now. And And so I listed out some of the things there, as I mentioned, as far as using a polishing machine to terminate that, and you know, some of the other differences. But the key ones really are just the fact that it is replaceable and that it is configurable and it's a very flexible design. So, you know, we're not trying to direct which way that it will go specifically. It's more, okay, what does the market require? What's needed out there, which we think is more reliability in the interconnect, and where would you like it to go? Like, what kind of a connector system? So we have it for 3 or 4 different connector systems now, and you know, more of those will follow as demand comes up. I guess one of the differences I should mention is that with any of the traditional systems, they're all using a face alignment technique, so that if you have any dust or dirt in between those faces, then the angle will come off, and they're very sensitive to angle, so you'll get a lot of loss. So you have to actually clean you don't have to clean the lenses so much, you actually have to clean the connectors so that those metal faces are perfectly flat and optically flat and aligned to each other. On the contact, it's actually a round cylinder, so as you plug it in, it scrapes off the dust and any kind of contaminants on there, just like a kind of a copper connector. So you don't really have to worry about the cleaning so much. Some of the testing that we did on the expanded beam contact, the ones that you saw over there, we call it the size 12, which is the larger contact. We did some insertion loss testing, and you can see that, you know, it's around 0.5, 0.6 is what we got. That's outside of the connector, just plugging them in randomly with 81 contacts there. Return loss on this one is greater than 60 dB for all of those contacts. So the technology on the video jack gets to about 45 dB, and then we took it to the next step on the contact, and it's 60 plus dB, because we have a double angle on the lens and the contact itself. And just as a quick example of where you can use an expanded beam contact, this is some people we actually met at NAB, but it's a medical company, and they make HD transmission equipment that uses a fiber and 2 copper, and they couldn't find any connector solutions that would work for that. They really wanted expanded beam because it's in an operating theater. They want nurses to be able to use it. They want to be able to throw it on the ground, you know, pull it by the cable, do anything with this connector and not have it ever fail. So we said, sure, you know, we'll develop a custom connector, and we did that because we already had the technology for that expanded beam contact, and you can see in there how it fits into the connector system. They wanted to make sure that if you pulled it out, it wouldn't rip the connector out of the wall, because they have you know, $500,000 equipment on these medical carts, and if they're driving them away, the nurses sometimes forget to unplug them, and they want to make sure that they'll pull out and they won't pull the $500,000 equipment on the ground, which happens, I guess, a few times. And then the final application that's most recent is the EL SMPTE connector. So these are the connectors that you see on the back of fiber cameras that are usually used outdoor. I know we have quite a few studios nowadays have them indoor as well. But anytime you're running fiber longer than a few hundred feet, or running HD longer than a few hundred feet, you are going to use a fiber camera. And these are, the form factor of this connector is the same as actually the Limo or the Canary or the King's connector. And what we've done is put the fiber contact inside that connector, so that if you put that on the camera, when you remate and mate, you'll never have to clean that connector. And that, with the SMPTE, that's one of the most difficult things, because those cleaning tools that were shown before, they don't work with SMPTE connectors. You know, you need a special cleaning tool that goes in there. And again, if you're out on the golf course, or you're out at the NFL, or you know, the NBA, or somewhere out in the field, you're not always going to have one of those cleaners around. And so you really don't want to be mating and demating the SMPTE connectors. And it's certainly the biggest issue with those, with that SMPTE 304 system. You know, you have copper, you have fiber in that very small space, and it's tough to clean those things. And anyone who uses those cables will tell you they have a pile of them in the corner that are dirty. You know, they don't really, there's something wrong with them, they're not sure what, and they'll send it back to the manufacturer and get them to repolish it or clean it. And you know, the aim of this is to eliminate that pile and and just have it so that you can mate it thousands of times and never have an issue. Now, of course, you have to mate expanded beam to expanded beam, so you have to change a pair of these. And again, for standardization, we've used the same technique so that you would have optical alignment. The optical signal will go down the middle of the contact, and so competitors could use the same or similar technology to mate, and so the different camera manufacturers can then implement that system. Sort of for the technical people inside there, I like to see the cutaway section of the connector itself, and you can see there's basically a tube, you know, just like we had on the original design of the original expanded beam contact. It's just been implemented into this connector system. So none of the actual components were changed for the SMPTE, for the latching, for the delatching. The only thing that's changed is actually the contact. And so if you had a King's connector, or even if you had somebody else's connector, as long as you can get that contact inside there, the pair of them, then that'll operate. So, you know, in summary, basically we're talking about fiber getting into broadcast. Now that we're in the, you know, the 3 gig world, there's a lot of fiber needed in there. But if you go into any studio, you'll see maybe 1 fiber rack and, you know, 20 copper, you know, maybe 2 fiber and, you know, 50 copper. And so as the years go by, you know, the amount of fiber racks you see is going to be more, and the amount of copper ones you see is going to be less. And, you know, it's already really happened in the telco world and in the datacom world. As they hit 10 gig, that's really when things changed over. And that's really what's happening now in the broadcast world, is we're hitting that 10 gigabit limit, and it's all going to switch over all of a sudden. And so our thesis here is that the need for reliability is going to increase greatly. And you know, this is one solution, we think, to that need. So thanks everybody, and if you have any questions, please ask away. Yep. Back.
Is there any potential for eye injury working with active?
Yes, actually, that's a good point. And on the video jack, we have a shutter system in there, so that when you take out the patch cord, you know, the shutter flips up and nothing comes out of the hole. So if you're looking in the video jack, you won't get it in your eye. With the expanded beam contact system, you know, if you look down there, then you would have a potential for an eye injury. I mean, similar to any other connector, but because it's expanded beam, it is much more focused, and you know, you would have to make sure that you don't look down that hole. And I mean, similarly with any high power laser or any high power system, especially some of these, you know, 0 dBm systems, you can't hold it up to your eye and look at it. So that is something definitely to be aware of. And we used to have a label on our video jacks to say, you know, be careful, don't look in here. But then we implemented the shutter, and you know, we took the labels away. But certainly any open connector, you would have to be aware not to look down there. Okay. Yeah.
Earlier we spoke about a 0.5 dB loss per connector.
Yep.
Is that due just to the interface of the 2 connectors, or doesn't the connector itself interfacing to the fiber on either side have some loss there too?
Yeah. So he mentioned, you know, that we have 0.5 dB on a single mode connection that is physical contact, and usually it's a lot better than that. You know, and it's caused by the offset of the core of the fiber. That's the main cause. So if you have 2 connectors that are perfectly clean and they're mated perfectly well, then the only loss that you're going to see is offset between the cores. So it's really the tolerances in the ceramic, the tolerances in the fiber, and all of that. And they're very good. So usually you'll see 0.1 to 0.2 dB, but you have to allow for 0.5 because usually there's a little bit of dirt, there might be some dust and that sort of thing. But so that's a physical contact. But on the expanded beam, you have more things in there. So you have a lens, you know, you have another interface. So as the light exits from the fiber, you're going to lose like some light. And then as it enters the lens, you're going to lose a little bit there. And then as it exits the other lens, you'll lose some there. But what you do to reduce or eliminate that is you do an optical coating. So basically you go from about a 0.2 of a dB at each interface to about a 0.02 dB. So it all adds up. You have 8 interfaces, so that's about a 0.8. So actually, 0.16 just in inherent losses, but then you also have alignment losses. So so what I showed you before about a 0.5, that's very good for expanded beam connector. Normally you'd see about a 2 dB, just because you could never align all those optics together perfectly. But using this technology, it's now possible to do that. Okay, any others? All right. Oh, one over here.
Is anyone else jump on the expanded beam, or do you have a patent on it? Or?
Well, we have a patent on the video jack. Part of that is the alignment technique. There's some, like I mentioned here, that the military suppliers have kind of been on this for a while, and so they are offering contacts. I'm not sure about the patent situation as to whether there's any kind of infringement there, but I think it's not really that big now yet where it's a big issue, and at the moment it's more trying to get standards established so that it'll become bigger and more, I don't think there'll be a problem. There'll be 2 or 3 people who are in this, and it'll work out. So you have the Glen Air and Sabertech are a couple of those people who are in it. But again, I mentioned that they're not doing that much in broadcast with the contact itself. Okay, well, one more question here.
What cable manufacturers are using your SMPTE 304 connector right now?
Yeah, we have a couple of in distribution, and we're doing we're doing it basically ourselves and also through our distribution partners. So if you ask whoever your normal large distributors are, and you say, give me a King's SMPTE 304, they'll say, yeah, we can get that for you. But right now they don't have it, in stock. They don't have may not have a whole bunch of those. But you can also go onto our website and have a look at that if you're interested. Type in the part number, and you'll see who has it in stock.
Thank you very much.
Thanks.